All right, guys, Mr. Antonucci here, and in this video, we're going to finish up section 2 on analytic techniques for finding limits of functions. And in this video, we're going to look at a couple more theorems as well as average rate of change in the difference quotient. So let's start with limits of rational functions and quotients. First theorem here that f and g are functions for which the limits exist, then the limit of the quotient exists, and the limit of the quotient is equal to the quotient of the limits. In other words, you can take the limit of the numerator and denominator function separately, get those answers, and then whatever that quotient ends up being. However, you can't do it if the limit of the denominator function ends up being 0. So just be aware of that. Now, a corollary or a result of that is the limit of a rational function. Now remember, rational functions are functions where the numerator and denominator are both polynomials. And remember our theorem previously that the limit of a polynomial can be evaluated using direct substitution. Well, since a rational function is just a polynomial divided by a polynomial, then we can use direct substitution here. Again, provided that number that we're taking the limit toward is in the domain of the rational function. Again, if the denominator is 0 at that point, then the rational function will be undefined. So here are a couple examples. We'll take the limit as x approaches 1 of 3x cubed minus 2x plus 1 over 4x squared plus 5. So the limit is just going to be 3 times 1 cubed minus 2 times 1 plus 1 all over 4 times 1 squared plus 5. And that's going to be 3 minus 2 plus 1 over 4 plus 5. So that's going to give us 2/9. For the next one, we have the limit as x approaches -2 for this rational function. So we can try direct substitution. So 2 times -2 plus 4 over 3 times -2 squared minus 1. So the numerator in this case is going to be 0, and as long as the denominator is not 0, we're okay. So -2 squared is 4 times 3 is 12 minus 1 is 11, and we get 0. It's okay that the limit is 0. You just can't have a 0 in the denominator. And one more here. Now here we have the limit of a radical function over a polynomial. So we can't just use direct substitution, but we can use the quotient property, which says we could take the limit of x approaching 4 of 3x squared plus 1 over the limit as x approaches 4 of x minus 1. Now, since the denominator is a polynomial, we can use direct substitution. You plug 4 in, you get 3. Here in the numerator, we could use the limit properties to break apart the radical, the 3x squared plus 1, and we would eventually see that the limit is going to be square root of 49 or 7, so our answer is 7/3. So one thing I just want to point out is that you will not be expected to write step-by-step proofs of limits of functions by breaking down the limits into all of its separate properties. You may be asked to do that once in a while on like a homework assignment. In general, you're going to want to use direct substitution as your first step, and if that doesn't work, then try one of these other techniques that we're going to look at here. And one of the situations is when direct substitution fails. Remember, the quotient property for limits can only be used when the denominator is not 0. So there's a couple strategies we have at our disposal when the limit of the denominator is 0. So for example, in this case, as x approaches -2, the denominator would be 0. One of the strategies we have is creating an equivalent function that is the same as the original function at all points except that one limiting value. And how we do this with polynomials and rational functions is we could factor it. So you take the limit as x approaches -2. The denominator is a difference of squares, so that factors into x minus 2, x plus 2. And the numerator, I need factors of 6 that add to positive 5, so that'd be x plus 2 and x plus 3. And notice you could cancel a factor of x plus 2, which is essentially canceling the problem with the denominator. So then we would have an equivalent function, limit as x approaches -2 of x plus 3 over x minus 2. And you can verify this graphically that these two functions are the same exact function except at x equals -2. And as x approaches -2, you would have 1 over -4. And that limit would be -1/4. Next situation that can happen is whenever you have radicals. In this case, you can't really factor, but we do have a strategy which is called multiplying by the conjugate. And just to verify, in this case, if you directly substitute x equals 5, you would have 0 in the denominator. So don't immediately go to these strategies. Try direct substitution first, because sometimes that does work. The conjugate is formed by taking the two terms that are being added or subtracted with the radicals and changing the sign in between. So we would have square root x plus square root 5, and then you have to multiply by that over itself because you want to essentially multiply by 1, and this fraction is equivalent to 1. Now we would have the limit as x approaches 5. When you FOIL conjugates, the firsts multiply and you just get x. Then the outers and the inners multiply and would cancel each other. You would have plus root 5x minus root 5x. And then when you multiply the lasts, you would get minus root 25 or minus 5. So that's foiling the numerator. And then the denominator, you wouldn't FOIL that out here. So we're just going to leave it as is because you can now see that the x minus 5s are going to cancel. Now be careful when you cancel and everything in the numerator cancels. Sometimes students accidentally just forget to write the numerator. But remember, those are essentially dividing to 1. So we have 1 over root x plus root 5. And as x approaches 5, you'd have 1 over root 5 plus root 5, which is 1 over 2 root 5, not root 10 or anything like that. And again, you could verify graphically that this first function and our simplified function agree at all x values except x equals 5. And then one more situation that may come up is with complex fractions. Here, if x approaches 0, not only is the denominator here 0, but the numerator is going to be 1/3 minus 1/3. What we do is we multiply by the common denominator of the numerator fractions over itself. X plus 3 times 3 over x plus 3 times 3. So when I multiply this, you have to distribute it to both terms in the numerator. So you have limit as x approaches 0. When I distribute the x plus 3 times 3 to the first fraction, the x plus 3s would cancel and you would just have 3. When I distribute it to the second fraction, the 3s will cancel and I would have x plus 3. But be careful because we have this negative here, so we're going to subtract that x plus 3 and put it in parentheses so we know we're subtracting the whole quantity. The denominator, we're not going to distribute it out. We're just going to rewrite it as 3x times x plus 3. And at this step, you might be tempted to cancel the x plus 3s, but you can't do that because it's not multiplication in the numerator, that's subtraction. So if we write that out, limit as x approaches 0 of, this is going to be 3 minus x minus 3. So you would have negative x over 3x times x plus 3. And the x's will cancel, leaving you with the limit as x approaches 0 of -1 over 3 times x plus 3. And if you take the limit as x approaches 0, then you'd have -1/9 as your answer there. All right, the next thing I want to talk about is a limit of an average rate of change. An average rate of change is basically the slope of a function between 2 points. So if I do this in general, some interesting and neat things happen. So I want to find the average rate of change of f of x equals x squared plus 3x from 2 to x. So generally speaking, if I want to find the average rate of change, that is equivalent to change in y over change in x, which in terms of function notation is f of b minus f of a all over b minus a. That's kind of like your y2 minus y1 over x2 minus x1. Well, in this case, b is equal to x and a is equal to 2 because it says I want to go from 2 to x. So what I'm going to do is write f of x minus f of 2 all over x minus 2. So the function f of x is just x squared plus 3x minus f of 2. Well, when I plug 2 in, 2 squared is 4 plus 3 times 2 is 6, so I would get 10 all over x minus 2. So this expression here is going to give me the average rate of change of the function f from 2 to whatever x value it is. So if I want to plug an x value in, I can automatically grab the average rate of change of the function. So for part b, I want to take the limit as x approaches 2 of the average rate of change. So all I have to do is take the limit as x approaches 2 of the x squared plus 3x minus 10 over x minus 2. Now, if I plug 2 in directly, that's going to give me undefined because the denominator would be equal to 0. So one of the steps we just learned is factoring. So I need factors of negative 10 that add to 3. So x plus 5x minus 2 over the factor x minus 2. And the x minus 2's will cancel. So now I can take the limit as x approaches 2 of x plus 5. And as x approaches 2, this limit is equal to 7. So here I have the function x squared plus 3x. It's in red. And I also have the line that connects the 2 points between the point 2 comma 10 and some other point at whatever the x value is. Now I can move this point around a little bit. But notice, if I take the limit as x approaches 2 by dragging this point closer and closer, I have the expression for the average rate of change here. Notice what this value gets closer and closer to. Gets closer and closer to 7. So graphically, that's what we're doing. This line that connects the 2 points is called the secant line. And as I drag this second point closer and closer to the first one, what I'm doing is I'm approaching what would be called the tangent line. And this average rate of change is approaching what the slope of the tangent line would be at that point. So this leads nicely into a discussion of what's called the difference quotient. The difference quotient is just exactly what it says. It's a difference inside of a quotient. So it's a subtraction problem in the numerator of a fraction. And this actually forms the foundation for what we call differential calculus. And we'll study that more later on, but for now, we're just going to introduce the concept. So the difference quotient is f of x plus h minus f of x all over h. And where this comes from is f of x plus h is kind of like our second point, that's our y2. F of x is the original point, that's like our y1. And the h is just our change in x. So for example, if I want to find the difference quotient for f of x here is 2x squared minus 3x plus 1, I would start with figuring out first what f of x plus h is. That's just 2 times x plus h squared minus 3 times x plus h plus 1. I'm just substituting x plus h in anywhere there's an x. So next thing is we would FOIL the x plus h squared, and you get x squared plus 2xh plus h squared. Then we could distribute the negative 3, so minus 3x minus 3h, then the plus 1. We have to distribute this too, so now there are no like terms in that expression. The numerator of the difference quotient is f of x plus h minus f of x. So we would take all of this and subtract from that what f of x is. It's 2x squared minus 3x plus 1. But again, be careful, you're subtracting that whole polynomial, so you want to put it in parentheses. Then you can see some things start to cancel. If I subtract a 2x squared, it's going to cancel with this one. If I subtract a negative 3x, it would make it positive 3x, so it's going to cancel with that other one. And then subtracting 1 is going to cancel the 1's right there. So if we simplify this down a little bit, minus 3h all over h. Remember, we did not write the denominator of the difference quotient yet. Now notice each term in the numerator has an h, so if we factor an h out, and that's going to cancel with the h in the denominator. So we have 4x plus 2h minus 3, provided that h is not equal to 0. So that is part A. Now for part B, we want to take the limit as h approaches 0 of the difference quotient. Well, we already did all the hard work up here of setting up the difference quotient and simplifying it. So now all we have to do is take the limit as h approaches 0 of 4x plus 2h minus 3. Now don't let this fool you. The x is still a variable, but we're not letting it vary at all. All we're doing is let h approach 0. So as h approaches 0, everything else kind of stays the same, and you have 4x minus 3. All right, guys, that's it for this video. Hope that was helpful. Again, reach out if you have any questions, and take care.